Okay, so this talk is going to be about explainable AI, and as alluded to by Professor Yang in the previous lecture or talk, he taught about one of the problems of deep learning is the interpretability, right? And his approach I would classify as a kind of a global interpretability, where we try to see how the overall function behaves. What is the mapping reduced to? How is it reduced the data into a set of centroids and with particular radius and the separation of the classes. Okay, so that's a global explanation. And in this talk, we'll focus more on a local explanation, which means given a particular input and output that I present to the neural network or DNN, I want to know why the neural network made this particular decision. What were the features or what were the important parts of the image or the input that are actually used to make that decision? Because I want to know something about why it came up with a potentially wrong decision, or maybe there's a problem, some corner cases that might appear, and I want to investigate whether it actually works. Okay. So that's the first part of the talk. And then the second part of the talk is we'll look at XAI, but the current XAI is developed only for developers or experts in AI, okay, but it's not developed for humans. By humans, I mean end users or stakeholders of AI. Right. So in the next part of the talk, I will discuss some initial works on how we can build a human-compatible version of XAI, which is more useful for the end users. So we basically take the human into the loop of XAI. Okay. So in this talk, I'll mainly be talking about object detection because we're interested in autonomous vehicles, and object detection is one of the fundamental technologies using that to detect, cars and people in front of the vehicle. Okay, and for those of you who don't know, so object detection is this classical problem where we want to find the position of each object in a particular image, and we have a set of objects that we're interested in. Okay, and here are some examples of results. Okay, and this is used in self-driving cars and medical diagnosis. It's also used in your phone when you take a picture, it finds your face. Okay, so how do these object detectors work? So very briefly, there's essentially three types. The first is called a two-stage detector. So I have an image, I extract some feature maps using a backbone network like ResNet. Then given that high-level feature map, I combine them together and I try to predict locations where there might be an object. Right, so this is called a region proposal. Okay, and then given those region proposals, I predict whether or not it's an object and what class that object is. And I also predict where the actual bounding box is around that object. Okay. That's two stages. Two stages are region proposal and classification. Okay, there's a simplification of this called a one-stage detector, where you predict everything in one go. You predict the region proposals and the classes at the same time. Okay, that's a technology a few years ago. Now there's transformer-based object detectors, and the pipeline looks like this. So again, we extract features like before, but now instead of using a CNN decoder to classify different objects, we use a transformer encoder. Okay, and this transformer encoder produces a set of features here. Then we have object queries that are learnable, and we have a transformer decoder, which take those object queries and converts them into predictions of object and the object class. Okay. Okay, so of course, to train these models, we use a lot of data. We use a big data set of maybe 100,000 images. That's a class MS COCO data set. Okay, and these deep neural networks are actually quite large. So this DTER model has around 60 million parameters. Okay, and if you calculate, how many actual operations it does 250 billion mathematical operations per image to just tell you where those objects are. Okay, but the problem is that we designed this high-level architecture like this DTER, this pipeline, okay, and then we just let it go. And then we say, okay, just learn from the data from this. And whether or not this architecture is correct, whether the biases that we put into the architecture is useful or not, kind of depends on the data. And we just let it go, and then we're done. Okay, but as a scientist, we have actual questions about whether this is working. Okay, and the actual internal workings of each block is very hard to interpret. Okay, and this really limits what we can do. Okay, so for developers, that limits our ability to debug and improve the models. Because given the output is wrong, I don't know why the output is wrong. I just know the output was wrong, and somewhere inside there's a problem. then what can I do? I can play around with parameters, I can add more data, I can change architecture, right? But this is all shooting in the dark, right? Hopefully my solution works. Okay, it also limits the end user's understanding and trust in the model. So I'm sitting in my car, it's detecting a car coming at me, hopefully. Now I want to know whether, can I trust the detector in this vehicle to tell me that that's really a car, right? And will it stop the car, stop my vehicle or avoid that car, right? So there's an amount of trust here that needs to be built between yourself and the self-driving vehicle, that's the end user. Okay, and also limits how the regulator can regulate or understand the safety issues or failure modes of those models. Okay. So the question is, how can we explain the internal workings of the detector, right? And we need to be able to explain for different users, for developers who know about AI, who understand deep learning, and for end users, maybe your grandma who knows nothing about AI, but wants to at least be able to trust the model. Okay. We also need to explain effectively. That means we need the explanation to be maximally informative, but we also need it to be efficient, meaning that I can present it to you and you don't need to think very much. You don't have a high cognitive load in order to view that explanation, understand what's going on. So this is important, again, in your self-driving car, the vehicle gives you an explanation, right? And if you have to think too long, it might be too late, whether you trust it or not. Okay. And the final question is, how can we induce understanding and trust between human and model? Okay. So in the first part of the talk, I'll first discuss some of our work on doing XAI for object detectors, and then I'll talk about this next generation XAI, where we hope to put the human into the loop. Okay. So first of all, a classical way to explain deep neural network is to use something called a saliency map or heat map or attribution map. So the idea is like this. So we have an image, image classifier, a DNA, and we get a prediction. So we want to construct this saliency map, which reflects how important each pixel is in the image to the prediction of the lion class. Okay, and here's an example. So the red here denotes high importance pixels, and the blue denotes low importance. So for this particular classifier, it finds the face of the lion to be the most informative, the face of the large lion, but not the face of the cub. Okay. So the way that we can do this is, one way to do this is based on the gradients of the model. So we take a gradient of the lion class with respect to a feature map inside the model. Okay, and then we multiply it by the attribute, the feature map, and then we get this saliency map. This is called GradCam. Okay. The problem is this is for image classification, and if I apply this directly to object classification, it doesn't work because the previous methods, they aggregate all of the class information together, all the spatial information together for one class. So if I try to apply this GradCam model to object detection tasks, so I want to know why the model predicted this as a person, then it will highlight features that are on other people, right? Because it mixes all those features together. Okay. But object detection is also more interesting in classification because it does multiple things. So it predicts whether there's an object there, it predicts the class of the object. It also predicts where the object is, the location of the bounding box. Okay, so there's actually multiple things that are important. One is the object specification, which means what regions are important for predicting this class. For example, this is important for predicting the class. This location is important for predicting the left part of the bounding box, is important for the bottom of the bounding box, the right and the top. Okay. Another important thing is object discrimination. That means if I have two objects that are overlapping, I want to know which object was actually detected. Okay, so here's an example. I have, I don't know, 5 or 6 people kind of partially occluded, right? And here are different detections from my original detector. Okay, and for this one, can you tell me which person this detector found? Not really, because there's red highlighted regions on 3 people, right? And this one, there's on 2 people. This one's on 1 person. So maybe this one is just this person that's not here, but I don't know if this detection is finding the person behind or not. Okay, so it's difficult to discriminate using the saliency map, but we can improve the saliency map to make it easy to discriminate by making the model focus on particular parts of the object when it's doing the classification. So this is an example from our method where we can create easier to discriminate objects. Okay, so how does it work? So this is our object detector activation maps. So here's an example of image. We extract some features. These are the feature maps. Then we have the head that predicts the class label and the bounding box. Okay. So to construct the heat map, we simply take the gradient of one of these predictions, like the class score with respect to the feature map A. Okay, and then we multiply by the feature map A, and that gives us explanation H. Okay, and this H is actually an approximation of a first order approximation of the output Y here, in this case, a class score. So if I just sum up over all of the spatial indices IJ, I have an approximation that this should be the output of the model. Okay, so it's like a linear approximation at that input. Okay, these important weights are according to the gradient. Okay, so this is the final saliency map that we use. This is the gradient times the activation map, and then we use a rectified linear unit here, means that we just focus on the positive components of this heat map. That means that we're interested in the features that improve or boost the classification score of this object, the ones that are correlated with the score of the object. Okay, so here are some examples when we apply this to a one-stage detector. Okay, so this is the image, and then these are the different explanations for the different parts of the detector. So I think this one is kind of interesting. So this is the motorcycle. Right? It uses the wheels and kind of this part to detect the motorcycle. And then the back of the motorcycle is the bottom is based on the bottom wheel, the back wheel, actually, not the front wheel. Okay? And the right side of the motorcycle depends a lot on where the person is, the contact point of the person and the motorcycle. And if we look at the person on the motorcycle, then it finds that the important part is actually the legs of the person, right? And the feet determine here the bottom of the person in this. Okay, so in this case, we get some reasonable explanations. Okay, but we can also get we can also find some problems. Okay, so here is an example of a surfboard, and these are different proposals that were generated. Okay, and this is the true surfboard, okay? And this is another prediction of surfboard where it uses the back of the, I think it's the sand in the background as part of the surfboard, because it looks like the wave. So it infers that there's a whole surfboard here. Okay. This is another example. This is my favorite example. So this is a toilet. Okay. And of course, it classifies it correctly as a toilet. Right. And you can see it uses the lid of the toilet as the most important feature to classify as a toilet. But in this image, there's a reflection of the toilet in the glass here. You can see that. And it classifies this part as sink. Okay. Because it's a shallow bowl. Right. And it classifies it sink because normally for it to classify as toilet, it has to have a back of the toilet. So this shows you that there's some bias in this data set. So all the toilets have the lid up and not a missing lid. Okay, so this object detector won't work if you go to a public bathroom because they don't have these lids. But it also shows the kind of importance of doing this kind of analysis. Okay, this is just a comparison with other methods. So the other methods are class-based, so they always highlight multiple people of the same class, where ours will highlight the person here, right? And this is a detector-based version of a perturbation method. So perturbation method means I remove some parts of the image and see whether or not the class score changes. If it changes, then this part of the image was important, and I can map it out. But the problem with perturbation method is it requires a lot of sampling. So how many samples you generate determines the smoothness, and also how big of the perturbations you use, like how big the rectangle or circle you use, also matters. So in this case, although this is designed for detectors, it does worse because it has this randomness associated with it. Okay. Another question you might have is, how does this work for transformer-based models? So transformer-based models have this self-attention operation. Okay, and it's important to note that self-attention is a bottom-up attention. Okay, it means it has no idea about the ultimate prediction. It just looks at the local features, decides what it thinks is important, and passes it to the next layer. Okay, so the highlighted features from transformer self-attention are not necessarily used when it generates the output. Right? It's just used in the inference process, but that may not depend on the output. The output may not depend on it. Okay, so here's an example of a transformer-based model teacher. Okay, these are the self-attention after the encoder. Okay, and then this is the self-attention after the decoder. Okay, so you can see maybe for this person, right, it finds that these features are important. Okay, but in our method, because we can tease out different outputs, and our method is actually looking at top-down attention, we're seeing what features directly affected the output. Okay, then we can separate it into different features so we can see what are the features or parts of the image that were important for different predictions, like the left, top, right, and bottom of this person, and also the class. Okay, so our method can work in conjunction with the transformer-based methods. Okay, so in terms of evaluation, those are some qualitative results. For evaluation, we use something called faithfulness, which means we use a saliency map as a rank of different pixels. Okay, and we have two tests. One is called deletion test. Deletion means that we use the ranking of the saliency map to remove pixels from the image, and then we try to see the drop in the accuracy of the model. Okay, the opposite is insertion. That means we start with a blank image, and then we insert the most important pixels first, okay, and then we record the increase of accuracy. Okay, and then we can summarize this using the area under the curve as we introduce more pixels or remove more pixels. Okay. So here are the results for these different models. So the deletion score we want to be reduced to lower, and insertion score we want to be higher. Okay, and of course, our model does better. Interesting. More interesting is we got interested in whether, so this model is better, but we don't know if it actually is useful for humans. So we started to do some user studies about how this model actually behaves in real performance with users. So we use a user trust study, okay, and the users had to rank the methods according to most reasonable and least reasonable. Okay, and they were given 120 images, and we got 40 users, 10 response per image. Okay, these are some examples. Okay. So if we rank the explanations, then in our trust survey, our method was ranked first around 53% of the time, okay, and second for 35% of the time. And the average rank was 1.6. So our method is substantially or statistically significantly more trustworthy than the other explanation methods. Okay. Another thing we can look at is, well, it's more trustworthy, but why is it more trustworthy? Is it related to something about humans, or is it just the model is better? Okay, so we're interested to see whether the saliency maps that we generated, whether their similarity to how humans perform the task is related to the user trust. Because if something performs more similar to you, then usually you will trust it implicitly. Okay. So here we use the AICIT study. We asked a human participant to explain the object within the bounding box here. Right? And then what they have to do is they have to look at the different features and then explain what are the most important features. Okay, and the idea here is we ask them to explain because we want them to actually look at the important parts, right? And that creates a saliency map if we aggregate over humans. So this is a saliency map for humans. Okay, and then this is the saliency maps for the XAI models. Okay, and then what we did is we could compute the correlation or similarity between the human and the XAI similarity. Okay, and our method had higher similarity than the other methods according to different distance metrics. Okay, but more interestingly is if we can look at a correlation between the similarity of the eye gaze to the saliency map, the XAI, versus the rank of how trustworthy that particular instance was. Okay, and we can see this nice correlation, which is the more similar the XAI method's saliency map was the human's eye gaze, the human strategy, the more trustworthy it was, the lower the average rank. Okay, so this is one of the first results where we can actually show that there's this implicit trust. If the model behaves similar to human, then we trust it that more. Okay. So this is the first part about object specification. And now we can move on to the second part, the second aspect of object detection, which is discrimination, because we have multiple objects in the scene. Okay, and the main question here is whether and how to tell which object was detected. Okay, and here we have different saliency maps for different detections. And from this, I could not really tell which object was, which person was detected. Okay, but we can use our XAI method in the loop of the training. So what we do is we have different ground truth here, different ground truth labels. Okay, and if these boxes correspond to different people in the ground truth, then I want the saliency maps generated from the model for this particular instance to be more separated. Okay, and if these two boxes correspond to the same person in the ground truth, okay, then I want their saliency maps to be consistent. Okay, so we can turn this into two regularization functions. One of them encourages separation using cosine similarity. The other encourages consistency, also using cosine similarity. Okay, and then we can insert this into the training process. And what it does is actually will modify how the detector works, right? The detector will try to find features that are helpful for detection, but also will be consistent or separated from other objects. Okay, so we're actually modifying how the model works using the explanations it generates during training. Okay, and here's an example of the results. So this is the original model, okay, and then this is with our training method. Okay, and these are different methods to evaluate discrimination. Maybe the most important one is this object discrimination index. Okay, this is the fraction of heat map within an object compared to outside object. Right? And once we do the training, then we can improve this substantially. Okay, we can also do a user study to see the real effect of this. Okay, so in the user study, we presented images of saliency map and here, the saliency map and the image, and then the user has to mark which person they thought was detected. Okay, and then we compare that with the ground truth. Okay, and then they can also rate their confidence of their prediction of the detection. Okay, so here are the results. There are two things that are important. The first is if we look at the confidence. So before the original method, around 70% of the time, it was confidence 5 most confident. But after we introduce this discriminability, then the confidence improves a lot more, right, by around 13%. Okay, the accuracy also increased a little bit. Okay, but the accuracy change here is not as much as the confidence change. So in general, this discrimination ability can improve the trust by improving the confidence in the detector. Okay. So these are two aspects of object detection, but this AICIT method, we can actually use it for other things, right? Because it provides some diagnostics about what is actually going on in the model, right? Not just the user studies. So here I talk about 3 applications. The first one is called a special form of non-maximum suppression. So normally in these detectors, we'll get a lot of detections coming out, and some of these will be overlapping because they detect the same object. Okay, and the typical way to suppress those overlapping detections is to look at the intersection over union between the objects. So for example, here, I have 2 objects and the IOU is 0.66. So that means that usually the threshold is 0.5. So that means that they're overlapped too much, so I remove one of them. Okay, and here I have 2 detections. The IOU is below 0.44, so they're not overlapping, so I'll keep both of them. Okay, but this is not good if the objects are always like overlapping, okay, because we can use the heat map from our method to actually see what is the object that was detected. And then we can use that to do the suppression. Okay, and we call that ODM NMS. Okay, and the idea here is we look at the correlation between the heat maps. So if the correlation is high, in this case, then I know that they're duplicates because they're looking at the same parts of the object here and here. Right? And if the correlation is low, that means that they're looking at different objects. So in this case, the left box is actually on the person in the front, and the right box is actually detecting the person in the back. Okay, so this allows us to improve the detection recall of the model. Okay. Another thing we can do is knowledge distillation, which Professor Yang introduced before. So the typical knowledge distillation uses bottom-up features activation to guide the distillation loss. So I try to match the feature maps. But again, whether a feature was created or not, activated in the end may not be used by the output. Okay, that's just a bottom-up process. So we can use the top-down attention, the top-down knowledge from the AICIT method to know which features were most important for the prediction and try to do the distillation according to those features more. Okay, so we have a mix of bottom-up and top-down attention. Okay, so here's an example. This is bottom-up attention. This is top-down attention. And then we provide a mixture of them. Okay, and that mixture can improve the knowledge distillation performance. Okay, and the final application is we extended this to vision language models, CLIP. Okay, so if you don't know CLIP, CLIP takes two inputs. One is a text input, the other is an image input, and it maps them into a common embedding space and computes a similarity between them, called the matching score. I don't know what happened to the equation here. But anyway, we can apply this, we can extend our method to explain both the vision and text encoders of CLIP. Okay, so we can provide a saliency map of the image, and we can also provide which words were important for computing the similarity score. And here's an example of the results. So these are different image text pairs. These are the results. So some interesting things here. So here there's cats, right? And it actually only looks at the cats and the pairs of shoes, but the sitting and the top, it's not used in this computation of the score. So that means that CLIP in general is not looking at that information, right? The relationship between geometric relationship between objects, right? Or the action of what the object is doing, right? This is another example. Car with some surfboards on the field. So again, it ignores the word field. And it's mainly looking at car and surfboard. Okay. So in the final part of this talk, I will introduce some of our recent work that we're trying to explore. And the main idea here is that if we look at the current state of the post-hoc XAI, right, we're just using the visualization technique to reveal the operation of the AI, right? And our ultimate goal, the goal that we say at the end of the day in the introduction is that we want to improve the understanding of the model, right? The user's understanding of the model. Okay, but in this post-hoc XAI, there's no user, right? There's no idea about what the user thinks currently about this model. And what the user thinks about the model now should reflect how the explanation should be generated for that user. Okay, so we're not considering the mental process of the user. So how would the user perform the task? Right? If the model performs the same way as a user, we don't really need to explain anything. We just say it works just like you, and then you trust it, right? Another thing is, what is the prior understanding about how the user thinks the model works? Okay, and then what are the explanations that can best update the current understanding of the user? So we need to know the user's mental process in order to explain to the user what's going on. Okay, and this has a very interesting idea. So we conceptualize this as a dynamic interaction between a user and an XAI. Okay, and now we have a human in the loop, so we can borrow ideas or integrate concepts from cognitive science. And the key concept that we'll integrate is called theory of mind. Okay, theory of mind is a capacity of a human or agent to understand the beliefs or give attributes to another person when they're interacting with them. Okay, and this is something that appears in children, and you can test it. Before a certain age, they're not able to do theory of mind tasks, and then after a certain age, they can do it. Right? And this is really an ability that happens through social interactions. Okay, so when we generate the explanation, then we should generate according to the current user's understanding, which means the theory of mind of the human's theory of mind of how the AI works. Okay, but we also need to understand how humans and AI perform the task differently, so we can present examples that are counterintuitive to the human. Okay, so in this model, we actually have three aspects of theory of mind that we need to consider. Okay, the first is the theory of mind, the XAI's theory of mind about how the human performs a task. Okay, so here's the human performing the detection task, and this is the XAI's prediction about how the human would do it based on eye gaze. Okay, we have the opposite, which is the user's theory of mind of how the AI performs a task. Okay, so this is the current understanding of the user. Okay, so this is the XAI, this is the AI, does the detection task, and the user thinks that it does it in this way using a saliency map. Okay, but this thing is unobserved, right? It's within the human's brain, and the computer can't access that directly. Okay, so we actually have a third aspect, which is the XAI's theory of mind of the user's belief of how AI performs a task. Okay, so this is the model of the human. at its current state. Okay, and this is called a second order theory of mind because it's the theory of mind of the theory of mind of something. Okay. Okay. So with these three pieces, then we can propose a framework for theory of mind based XAI. And the framework looks like this. So first we need to compare the human and AI performance strategies. Okay, because the XAI needs to know the difference between how the user performs a task and how the AI performs a task in order to help update the beliefs, the current beliefs of the user. Okay, the second is we need to be able to model human strategy using machine learning because we need to make predictions on novel images about how a user would behave. Okay, and that predicted data can be used with the AI strategy to update the explanation. Okay, the third thing is that we need to create the XAI's model of the human understanding. This is the second order model. Okay, and this model will be used when I want to present examples. So I can look at the difference between our XAI's model of human understanding and the XAI's model of AI, right? And if these two differ, I can find examples that are most different and present them to the user in order for the user to update his mental model. And then from that, we can update our XAI model. Okay. So finally, yeah, that's what I mentioned here. So finally, we combine these things, and then we can select explanations that can reduce the misalignment between the XAI model of AI and the XAI's model of humans' understanding of AI. Okay. Right, so this is the overall framework, and we have some works in each of these pieces that are ongoing works, recent works. So the first is just a comparison of human and AI strategy for detection. So we ask human participants to do a detection task, and there basically are two types of explanations, strategies. One is explorative strategy, which means we look at more parts of the image, and one is a focus strategy. Okay? And if we look at the XAI saliency maps, so AI tends to also use an explorative strategy. Okay? So that means that sometimes we will match with a person's strategy, sometimes we won't. Okay? And we need to keep this in mind when we design our XAI. Okay? We also looked at the comparison of the actual strategies between human and AI for detection. Okay? And we found that the transformer-based models are more similar to the explorative strategy of humans, but the CNN models are less similar, or more similar to the focus strategy. That makes sense because transformers use all the contextual information. Okay. The next thing we need to do is to model the human strategy. So that's step 2. So we have 2 ways to do this. One is called a human saliency imitator. I basically collect a lot of data of images, humans looking at eye gaze of humans looking at the image, and then I can train a model that predicts a saliency map based on the image. This is called the HSI. Okay. Or we have another model, which is called a human attention guided XAI, where we can extract information from the model using XAI method, and then train the XAI method to produce maps that are most similar to the human attention. Now, this is an example. Okay. And then finally, the question is, how can we measure humans' understanding of AI? Okay. And we can do this using something called a simulatability task. That means that the user will predict the AI's behavior using a novel input. The behavior means the prediction of the class and also the features that were used. And we measure the features based on the eye gaze. Okay, and this simulatability has 2 types. One is called forward simulation. That means we just predict the output given an input. So here's an example. We just say which vehicle were detected correctly and which were falsely detected, and then the human just marks it. Okay. Another is called counterfactual simulation, which means we perturb the input a little bit. So we take an image and then we perturb this part, and then we ask the user whether the output would change, whether it would change from not detecting the van correctly. Okay. And at the same time, we extract the eye gaze. Okay. So this work is still ongoing, and we're hoping to have some papers coming out on this. We've run some tests already. Okay. Okay, so in conclusion, in this work, we first propose a traditional XAI method using gradient-based methods to improve the object specification and discrimination in detectors. Okay, and we also found association between user trust and similarity in eye gaze, which suggests that more similar strategies, if the AI has similar strategies to human, then it's more implicitly more trustable. And we also looked at different applications. Okay, and the second part, I introduced our kind of new idea, or by noticing that the current generation of XAI doesn't actually look at the mental process of the user, although in the end, the user is supposed to be using this XAI to trust them, to build their trust in the model. Right? And so we conceptualize this as a dynamic interaction between the user and XAI. And then we use theory of mind concept in order to create beliefs of the user and XAI's belief of what the user is doing and so forth. And this enables us, hopefully, to better select examples so that we can update the user's belief more effectively and also more efficiently with the explanations. Okay. So that's all for my talk. And these are some references, and I can take questions if you have any.
Okay, let's welcome some questions from the audience. Any questions?
Oh, I forgot to mention why this is related to information theory. Okay, so in this process, it's all about communication and understanding between agents, right? So what is the amount of information shared or understood between an AI and a human, right? So my current thinking is that here we can leverage some techniques or models or theories from information theory in order to put a mathematical model around this that's more principled. So if you have any idea, we can talk.
Yes, Linchi. Where's the mic?
Okay, so maybe I just ask. So, thank you for your talk, Antoni. So, I have a question regarding, you just mentioned the communication or the information transmitted among agents, because like in the information theory and communication community nowadays, so there's a research topic called semantic communication and semantic information theory. So they try to focus not on the traditional like the bit level of information. They just try to explore the semantic or the content information. So from the AI perspective, how do you understand, or do you have some new insight into your understanding of the semantic information or semantic communication? Thank you.
Okay, so so what I'll say is that for this idea, we're thinking in terms of, because this model is noisy, right? The world is noisy. So whether or not I present an explanation, then whether or not the human understands in the correct way, that's noise. So in the sense, we have an ideal model, which is the AI. We have an explanation, which is some approximation to the AI model. Okay. And then we have the human's understanding is also approximation learned from the approximate model. So each one of these steps introduces noise. Okay, so then the question is, how can we, reduce this noise or make sure that the two distributions are aligned, they have some understanding or maybe mutual information is shared between them. There's communication between them. So this is my understanding. This is still very preliminary ideas. Yeah, that's it.
Okay, so sounds interesting. So it's like the idea that you don't really try to evaluate the information base, but how they perceive or understand the information.
Yeah,
like
so the information could be
different perspective.
We can abstract it into a probability distribution.
Okay.
Right? Because these models essentially they map to probability distributions.
Then the mismatch.
Yeah, the mismatch in those distributions. Right.
Okay,
Yeah.
so thank you.
Any more questions? I've got a quick one. How sensitive is your recognition to the mobility of the object?
The mobility, you mean?
So if the object is moving, would it be more challenging in terms of you want to maintain the same recognition accuracy?
So typically, it can affect it if there's some motion blur in the image. Yeah, we didn't look at this specifically, but it's an interesting idea. So if we take a video and we apply the XI method, when it breaks down, we can see why exactly it did break down. So that's a kind of one of the applications that we're building.
Thank you. If no further question, let's thank Professor Chen again. Thank you.